All right, so section 10.5 is area and arc length and polar coordinates. And I'm going to create or show where the creation of one of our formulas is coming from. So some ideas behind what we're doing. So we would like to compute the area enclosed by a polar curve. Since such a graph is not a function, of the form y equal f of x, we cannot use the usual area formulas developed in chapters 4 and 5. And while we could convert our parametric formulas from 10.2, a simpler approach uses the following geometric argument. So we're going to think about this from a geometrical perspective. Okay, so do you remember when you did area at the very first time in chapter 4? And what you did is you sort of dropped all these rectangles. And you said, okay, I'm going to make rectangles. And if I make the rectangles skinny enough, then almost every slice looks like a little bitty rectangle anyway. The area gets close enough that I'm happy enough with it. And if we let our rectangles go to infinitely many rectangles, or equivalently, if we let our width of our rectangles go to 0, then we could find the area using limits. Does that sound like something you remember? So we're going to do the same sort of thing, except that we're not going to do it with rectangles. We're going to do it with pieces of a pie. Okay? So imagine a piece of pizza that you divided up infinitely many times into infinitely little slivers of pieces of pizza. That's the image of what we're going to do. Okay? So, recall. Now you're all hungry, if you haven't eaten. Recall that the area of a circle with radius r and central angle theta is the formula area equals pi r squared. And the area of a sector, right, that's the pieces of a pie, the sector of a circle with central angle theta has a theta over 2 pi ratio. Right, theta is the measure of the angle, 2 pi is the measure going all the way around. So the area of a sector is pi r squared, and then we multiply it by the ratio, theta over 2 pi. And if we simplify this, we see the 2, or the pi, canceling, and we see us ending up having 1/2 r squared theta. So it looks like there's no pi's in there because of the cancellation. Now consider the area enclosed by a polar curve. Defined by the equation r equals f of theta, and the rays, theta equals alpha and theta equals beta. I'm moving it. Where f is continuous, and positive on the interval from alpha to beta. So let me draw the picture. There's more to write down, but let me draw the picture of what we're describing, and then we'll pause for today, and I'll record the second video separately. So you imagine that you have this sort of a random shape, whatever it is, and we've got a ray that is an angle measure of alpha. So this is the angle measure alpha. And then you've got a ray that over here is an angle measure all the way to here, all the way to here, that's beta. And our angle theta is in between. Okay, so that's our pizza slice. It's not really a slice of pizza because it's not curved, right? This is not circular on the end like it should be, right? It's not. But if we subdivided it enough, much like when we did the same thing with our rectangles, it gets closer and closer to those pieces, right? So if I make my value even smaller so that I have these tiny little bits right in here, they get closer and closer to looking like the slices of pizza that really are sectors of a circle. So this is the image that we're creating, and we're going to have infinitely many ones of these little slices, these sectors, or you can say that the angle measure of the sector itself is becoming infinitely smaller, approaching 0. Okay, that's the image of what we're going to do.